be playing Turing Complete again. After a few months, has been a few months since I stopped playing. And the reason why I stopped before is that I didn't have as much projects. I think now might be a good time to finish it because I have some projects more under my belt. And I don't think I think I'm gonna separate 20 minutes for each one and just look at the solutions because the reason why I want to do this is I want to bridge the gap between the hardware and the assembly and then Rust. So I think this is a good time to do it. And the goal is just to go through the levels as fast as possible while still understanding what's going on and making sure that at least I try a little bit to force myself to think about it because that way I'm gonna retain more information, I think. And then watch the videos for the solutions. Hopefully they will have the solutions. If not, then I think I'll just spend more time trying to figure out one and then watch videos. But yeah. And then hopefully I can get up to the last level here, which is assembly. And then at this point, once I reach the final goal, there's still some other stuff they added to this, which has a lot of other things that might be cool to look at. And I think at that point I might watch videos on assembly, or I don't think I'm gonna code on assembly because that might take too much time. But my idea is to watch enough videos to understand how it works, the main parts, and then only then continue to do the Rust stuff because that I think that's gonna give me a much better understanding of how the memory works and it's gonna help me code better. Rust is gonna make me it's gonna make easier to code in Rust. Yeah, so I'm gonna put the timer for 30 minutes and I'm gonna try that level. If it's taking too long to find the videos, I might lower the time. Hopefully, I didn't look at these videos, but I remember, I think they changed some levels, but I remember there were videos that have the solutions. So if I can't find it, then I think, like I said before, I'm just gonna spend more time in one level and then watch the videos for the other ones. Just so I understand how the computer is built from the ground up, from bottom up. With 3 bits of input, there are 8 combinations. Make a circuit that selects one output for each of the 8 combinations. No more or less than 1 bit should be green at a time. So I already read this and I didn't understand the instructions really well. I'm not sure what I'm supposed to do because there are 2 different gates here. There are these ones and these ones. So I wasn't really sure which ones to use. But I guess it's part of the challenge to figure out. I remember the other ones. I I'm supposed to connect these ones through this in a way that uh, satisfies this truth table here. And then as you build, each component becomes part of the toolkit, and then starts building on that until you reach the final goal, which is to build the computer. I was watching some videos on about the hardware. Just I think I watched one or two only from Ben something, and I think I'm gonna watch those videos as well. I think I tried this one. It fails here, but I didn't understand why this fails here if they are turned off. So I don't get it. Maybe they have hints and I don't remember. Oh, this one is in case I want to build. I'm gonna try multiple different approaches. Oh, interesting. I think this didn't exist the first time I played. Yeah, I think I'm gonna look at the solution for this because I don't think I'm gonna make any progress. I don't understand the level well. I remember all of these levels were really hard as well because I don't have a lot of pretty much I don't have any knowledge at all on hardware except the basic concepts. So I understand the concepts really well, but when it comes to actually the design of it, I don't understand it at all. I just watched, I think, a couple of videos. I watched those videos before, but I forgot about them. And then now I watched, I think, two from this guy here. Oh, I'm not subscribed. Yeah, I remember watching this, but I don't remember really well the concepts. And the videos are really good. So I think I'm gonna watch this playlist, probably all the videos, and hopefully I remember this time. And then there was this other video here that was extremely good that I think I'm gonna watch again. It really helps understand the Rust system for our memory. Really good video. And this one I was watching about because they added this stuff, I think. There are more complex systems that actually represent closer to the way that computer, like the chips of today, I think, work. It looks extremely complex. It's actually crazy to think about that people built this with wires without having any idea of if it's gonna work or not. Which part I'm on here? Here. Yeah, I'm still on the arithmetic. Hopefully this works and he shows the solution. It kind of sucks that it's the levels are locked. I don't really understand because I think a game like this is more the purpose is not so much to play like a game. The purpose is more to, for, at least for me, to understand how it works. So I think you should be able to go through any level you want. And then obviously you wouldn't have the solutions for the ones that you didn't solve, but doesn't matter because the point is just to, and they should have hints as well or the solution for the challenges. I don't understand why they don't. I guess it's probably because it forces people to do. So maybe most people are not like me. So if they don't have the,
All right,
you
episode
know,
2, we are on to arithmetic and memory. We are just going to start off with binary eraser. So essentially what you need to do is just, it's going to give you a decimal number and you turn it into binary. gonna turn off the timer just so I can actually explain how binary works. In case you don't know. Great. One in binary. Well, obviously we got all the numbers displayed down here. 2. And there we go. It's throwing softballs at us now. Okay, 3. So obviously we can just add these numbers, 2 and 1. But if these aren't here, if the numbers aren't here, then it gets a bit harder. And we do have to do that later. So it's worth knowing now that binary is a base 2 number system. What that means, essentially, let me get Microsoft Paint up. So every value is worth 2 to the n power, where n is the digit. You start counting from 0. So if you're looking for the first digit in the series, which is digit 0, then n equals 0. Apologize for my... Alright, double trouble. Let's see what we get. This level has 4 inputs, output green when 2 or more of them are green. I believe this is just...
Even though this is not my level, I think I'm gonna go over all of them because you probably solved in a different way than I did, and I don't remember how I solved the previous ones.
a matter of OR gates. And
Maybe they changed the levels as well, but I think it would be hard for them to change the previous ones unless it's a minor thing, because the logic has to be the same.
or maybe AND gates. Also, why don't I have the 3-pin AND gate? Oh well. 3, 4, 1, 2, 3, 4, 5. I think just run each set of 2. I'm missing one. Alright, and then join these together with OR gates. We can use the 3 pins for these ones, and then a 2-pin to join these 2. Alright, let's see if it works. Nice. So essentially what we're doing here is just, what if I can space these out to make it more obvious what's going on? I hope that's good enough. You can see that every AND gate is just handling a set of 2 pins, and every set of 2 pins is getting compared. So there's these two, these two, these two, the outer ones, and the inner ones. So 6 AND gates, then 2 3-pin OR gates to combine those 2 into 2 sets, and then a 2-pin OR gate to combine these 2. Alright, so moving on. Next is odd number of signals. I missed the objective. Using a maximum of 3 components, output green only when an odd number of inputs are green. We've got 4 inputs. So what we can do here is what's called a half adder. Now it's just a matter of whether or not I can remember what that looks like. So we have a exclusive OR, and I believe an AND. Let me just wire these up. Alright, so that's okay. Side outputs, we just ignore that one, so we keep that one. I think we can do the same down here. Alright, and then we connect these 2 with an exclusive OR. Alright, let's test it out. So 1, so odd, then 2, even, turns off. Back to odd, even, even. Alright, it seems to be good at least for 2 at a time. Let's check 3 at a time. Hey, that's pretty good. Cool. So yeah, really I don't even need the AND gates, it's just exclusive ORs. So yeah, the exclusive OR, obviously, it only turns on when one signal is given, which is an odd number, and so it sends it through. And that each one of these exclusive OR gates combines 2 bits and will return if just an odd number of that subset is true. So like these 2 pins are a subset of the entire set, so it's odd, and so it goes through. And then you got the second subset of these bottom pins, so you send another one, and that sends it through. So you got one of each subset, and now those 2 subsets are combined together in this exclusive OR gate into the greater, the full set. And so that's why it turns back off. Hope I explained that well enough. Right, next, circular dependency. This is pretty much a gimme, or a freebie. Just what it's trying to tell you is that you can't have the output of some component feeding into its own input, because the computer will be unable to determine its state at any given time. And there's an exception to this that it'll show you later. Oh, I should have deleted that. All right, let's go right into the exception then.
I think this is one of the things that is very hard to understand, and it is something that I think makes a very not yeah, maybe a very big difference, but I'm not sure. I think it makes a very big difference when it comes to optimizing things, which is understanding how the code is translated into the components of the computer, what each thing is doing, and in relationship to operational system as well. And after watching these videos, I think I'm gonna have to watch this one specifically a bunch of times, because it's, even though I get it and I understand everything that the guy is saying, it's very dense still to think about these things. And it's something that I want to train as well, to be able to think about it as a code of what's actually happening on the low level, on the actual machine and the hardware. I think that's the reason why I wanted to do this today.
The delay line component.
But I'm not sure how long I'm gonna go, because, yeah, like I said before, it's kind of, um, it can take a lot more time, and I don't know. It's kind of hard to decide when to do each thing, even though I know that I have to do everything. It's kind of hard to decide when's the right time, the priorities. Hey, Edison, what's up, man? A long time since I don't see you.
So what we've got, I suppose this is just telling you about the delayed, not necessarily how to use it for to make a circular dependency acceptable. See it, like normally when we send that tick, it would just go straight through, but now it
I'm
gets
good, man.
delayed.
And you? Still coding? Learning?
Oh wait, I'm supposed to do it by 2 ticks, I'm sorry. There we go. Alright, let's go to counting signals. The output component of this level is a binary counter, where the first 3 pins correspond to 1, 2, and 4. Use the binary counter to count the number of signals. The solution of this level is not very neat and requires more components. Okay, I made a pretty good solution for this. So what we're going to do, it's going to look a little messier
Interesting.
than normal. But we're just going to run these lines out like that. And this is kind of technically called a bus.
And what do you mean by check? Do you mean the price? I have no idea what music is. Oh, I mean, I suppose you say music of like singing or electronic. Oh, nice. And what about the mining stuff? Did you stop that? I remember you were gonna do some mining or something like that. Yeah, I think with proof of stake is not gonna be worth it anymore. Yeah. Yeah.
It's like a series of wires running together. Okay, so like I said before with subsets, we're going to use two AND gates to combine the two subsets we have here. Just run them up here.
Oh, yeah, that's also a problem as well. But it's fine. It's not like you lose anything. Still have the hardware, so doesn't matter. Eventually it will come back and then the light goes lower and make money again.
Then we're going to combine this with an AND gate to create the full set. And that will turn the fourth pin on of this.
Yeah, but I wouldn't sell it now, I think. I think now they're probably gonna go low. I'm not sure if they're already low, but I think everybody's selling now because of Ethereum, so it's gonna lower the price, I think. Yeah, but that makes sense. Yeah. I'm not really even looking at that, but yeah.
This one. So obviously if there are 4 signals, it turns on 4. Boom. So now we need to make the exceptions. We'll move this down a bit. Give ourselves some space. So we're going to make a branch off of these two with an exclusive OR gate. So now we're saying
Yeah, maybe it's actually a good time to buy, right? Yeah, if it gets down very low, I might consider buying. Because I think obviously the most common thing, like common sense thing, is that people, once Ethereum actually goes to proof of stake, a bunch of people will have to sell because they have a bunch of GPUs and mining houses that they are not gonna be able to pay off. So that's probably gonna make it the price very low. But then I'm not sure if it's gonna be worth buying. But maybe because there's still other coins that are mineable. Yeah. And especially for the thing that I'm doing, I think it's probably gonna be a good thing. But yeah, I need the other stuff first, the hardware, and especially the hardware to run my own node. So, do you think so? I don't think so, man. At what price is Ethereum now? I think it's gonna go very low. I think it's gonna go. I think Bitcoin is gonna go either 18 or lower or something like that. I don't know what time frame, but probably by the end of the year. And then right after that, a couple of months later, it's gonna start going up again. That's what I'm betting on.
that if there is one of these subsets turned on, but not the other, then we run it through.
But obviously not financial advice because I don't study a lot and haven't invested anything. It's just what I'm assuming is gonna happen.
We're not going to run it through to a pin yet because there's more subsets or more logic we need to perform. So what we're also going to do is we're going to combine the two subsets with exclusive OR gates. Wire these all up.
Yeah, man, let me know. Maybe I'll run data analysis on them. I think I'm gonna run, obviously, because of the stuff that I'm doing. I'm gonna capture data from Ethereum mainly, and then I'm gonna look at chains that have Rust, and I'm also gonna combine those chains with the Ethereum data, and I'm gonna run data analysis on them. So if you have any coins, it might be a good idea, because I just can incorporate. Eventually, I want to incorporate as much as possible, obviously, but the hardware is not gonna allow because it costs money. So yeah, but be careful, man, because it's very volatile. Trading is just like poker. You can't really trust your results. You have to wait for the long term, and you have to ground yourself in a strategy and use data to track whether or not you're winning or losing. You can't just rely on the outcomes because then you're gonna lose.
There,
And most people are like that, so that's why people sell at the top and buy at the bottom.
the meter.
Hmm. Never heard
Right.
of them.
Then same thing with here. We need to combine these subsets with both an AND gate and an exclusive OR gate.
Oh, maybe meme coins are very high risk. I wouldn't go for them.
Try to make it look nice.
Because
Make it
there's
bigger.
nothing you can ground yourself in. Meme coins is a complete bet. Like there's no fundamental behind a meme coin. You can get really high or just flop. It's a lot better to invest in things that have fundamentals, in my opinion. Obviously, not financial advice, but yeah. So I think I'm gonna look at Solana and Ethereum mainly, and I think those are the ecosystems that are gonna grow the most on the next bull run. And if you're building on those ecosystems and you're paying attention to the what's going on in the industry, then you're much more likely to make money. It's a much better way to think about than just try to bet on some random coins and then see if it's gonna go up or not. Yeah, Solana is good because it's cheap, I think, for trading. But I'm not sure yet because it's kind of hard to set up the system, set up Solana CLI on Windows. Maybe they improved that. But there's also a framework that was called Anchor that you use to code in Rust in the Solana ecospace that wasn't working for Windows. So it's a little bit harder to make it work. I'm not sure if I'm gonna make the effort.
Okay. So if we have one turn on, it's going to turn on one exclusive OR gate. And then if we only have one of these turned on, then that's going to turn on this exclusive OR gate. So that means we can just run this one straight to 1, because it will only turn on if only one of these subsets is turned on. So we can see any one that we turn on will run straight through. You can kind of...
Why don't you start building things, man? It's a lot better. Especially if you are learning how to code already. Instead of trying to mine or bet on coins, you should probably build something. And then as a byproduct of that, you're gonna know much better which ones to go for, which coins to put money. Nah, man, it's not hard at all. You just break it down into smaller problems and you work at it. And then at the end of it, because it's hard, there's gonna be a higher barrier of entry, so you're just better off. Like people that can do hard things can do easy things, but people that can do easy things don't necessarily can do hard things. So it's always better to train yourself to do the hard thing, and then the rest is gonna come. If you keep chasing the easy thing, then you're gonna chase the easy thing forever. No.
follow the green trail to see exactly what's happening. See, it goes to both the exclusive OR and the AND. But only one of these will ever be on it.
Sure, send it. How did you make it? With software, or did you code stuff to make it? Do you have the link, or is a file? Try upload it on YouTube or something like that, or and then give me the link. Nice, man. How did you make it?
We made it through the good and
It's really good, man. For the first beats, I enjoy this kind of music as well, more electronic, let's say. There's also something that I wanted to do at some point, but I can't do it right now because there's too much stuff. But in the future, maybe. Yeah, why?
Now you see if I turn 2 on, then the
Are you
exclusive.
doing it for the views or because you like doing it? Mm. I don't understand what that means. Did you buy it Pro in SoundCloud or? Hmm. Yeah, I think that's a bad strategy, man. You're not gonna. I mean, you can win, but I think you shouldn't focus on that. Focus on creating the best music you can, and then naturally, as a byproduct of that, people will share it. You can't force people to watch your stuff. You have always to have to work on yourself, and if you're not getting the reward you want, then just focus on improving yourself. And then for the money, if you need money right now, then you should be probably doing something else and then doing music on the side until you have enough money.
Before turned
Because
on.
you can't really rush the process, right? So
But if I turn on 1 bit of each subset, then both of the exclusive OR turns on, but only the AND will turn on. So now we can combine that with our exclusive OR gate down there. Just using regular OR gate for that, kind of running out of space. Let me do that. And that goes to 2, because, 2 pins. This AND gate combines 2 pins that are in different subsets. So we got the first subset and the second subset. The 2 pins are from different subsets, which gets represented here. But if they're in the same subset, let's say the bottom subset are both on, then that is what gets represented in this exclusive OR gate. Goes to 2. I hope the explanation about subsets is making sense and sort of parsing the information by reducing the number of bits you're actually working on at any given time. So, they give us 4, but we only want to work on 2 at a time. We have gates.
a song specifically, no, but you can keep doing it and improving it, and then you share it with me, and then I'll listen and I'll tell you my feedback. But yeah, I would if I was gonna do that, I would probably create a YouTube channel as well, and then create a YouTube channel, create then the SoundCloud that you have, and use software, and then record yourself or stream yourself. Just the thing that I'm doing now, where you're showing people how you're learning, and don't worry about what you're gonna get. Focus on the process and becoming better first. That's always should always be the goal of, because otherwise it's just a weak strategy and mentality because you're gonna go through ups and downs. It's the same thing with poker. The more you focus on the hands that you're playing, the worse you play because you're not focused on the strategy. And with anything else, it's the same thing. So always focus on the music first if that's what you want to do, and improving that as much as you possibly can. And don't worry about whether people are gonna like it or not. And then after that, you can focus on a strategy of marketing and stuff like that. It depends. Don't there isn't answer to that. I think it's a very hard question. Is it worth it to stream? I have to think about because streaming is something that allows you to accomplish multiple goals at once, and you usually want to do things that are like that. So you usually want to spend most of your time doing things that are going to maximize your time the most, and I think streaming is one of those things. But it has a lot of downsides as well, so it can be dangerous. So you always have to think about very carefully. But if you're not one of those people, then you should probably just continue to work and then just post the music. It's dangerous because attention is dangerous. The more attention you get, and especially, yeah, if you get attention, you get power, then people come after you, and you have to play the politics, and there's gonna be a bunch of people that are trying to take you down or fuck with you, or even kill you. So, and once you, the thing about fame is that once you go, you can never go back. So once you become famous, it's very hard to not be famous again. And that's sometimes because people that are really, really famous, they have no privacy. It's also a downside. And sometimes it is one thing in your mind, and then once you get there, you realize that it's not what you wanted. But then you can't go back, so you have to live with that forever. It's the same thing with girls that do porn. It might seem a good idea at the time, but after that, the decision is done and they will have to live forever with that consequence. So it's very high risk, and you have to think a lot about that.
3 pins, but 2 is much easier to parse.
But there are also other ways to make money with music that don't involve you posting yourself. You can create a YouTube channel that is just generic and you create your own music and never show your face, or post music from other people, or I'm sure there's several different other strategies that you can apply, but yeah. But focusing on the views and the attention is not the best way to go about it, in my opinion. You're just gonna lose thinking like that because you're always chasing something you can't control, and then you don't build yourself.
In my brain, at least. So let's move on.
Thanks.
All right, the half adder. This is actually what I was referring to in the last one, or maybe it wasn't the last one, but one of the previous ones. Treat the inputs as 0 or 1 depending if they are off or on, adding them together in binary such that the result is either 0 or 1. As with normal addition, if the result cannot be described with 1 digit, set the carry to 1. So all we need is exclusive OR and an AND gate. So another reference to this subset theme. We only really have one, or not even really a subset. It's just a set. Just hook this up. One turns on the sum. Doesn't matter which one, but you turn them both on, and it turns on the carry. Now, a full adder, it has a third bit, and that's the carry. So, if you had multiple of these hooked up, you want the carry to
Nice.
carry over. All right, next up we have the full adder. So yeah, just the same thing we were doing before, but like I was explaining, we need the carry in. And, I'm actually going to move it up here and the carry to down here. I'll show you why at the end. Okay, so we need 2 exclusive ORs, 2 ANDs, and then an OR. We can go ahead and hook up the ANDs to the OR, then an input to exclusive OR, well, each input the exclusive OR. And this exclusive OR feeds into this one, and then the other pin comes from the carry. The carry also goes into this AND gate. I believe that's it. And
No.
yeah, that's it for the carry. The other pin from here comes from.
I try to stream often, but it depends. I don't really have a schedule.
It's exclusive OR. And then these 2 pins come from our inputs.
The point is just to do what I was talking about that you should do. But I'm not sure if I'm gonna go that route that I you want to go with. So, but I'm making sure that I'm building myself while showing other people. And then in case in the future I want to go that route, I can, because I have the history and I already have all the stuff that I built. And it's also useful to show other people that you spend a lot of time practicing a skill. So it's kind of like undeniable. It's way better than a resume, because people can watch all your videos and they will see that you actually spent a bunch of time focusing on that thing. Yes.
I guess I should have rotated that to come down here, but it'll be fine. Alright, so we send a 1, we get the sum. So it's like adding 1 plus 0. Add 1 plus 1, and we get the carry. And then add 1 plus 1 plus 1, we get sum and the carry. So that's like dropping the 1, carrying the 1. So the reason I stack this carry vertically,
No,
exactly where the
not a
carry
pro
in is also
Turing.
the reason I did that is
Turer.
because in a ripple carry adder, you've got multiple of these. So then you'll have one like down here, and here, and so on and so forth. And every one of these handles 1 bit of the byte, or however many bytes you're feeding it. And so yeah, that's just how you would construct it. Boom. All right, moving on. All right, double the number. Quite possibly the easiest challenge out of this set. You get these new tools. You get a splitter and a maker. And literally all you do is take the 1 from this one and wire it to the 2 of that one. 2 to 4, 4 to 8, so on and so forth. Oops. So, simple as. Alright, odd ticks. I don't really remember this one. Delay line is allowed to depend on its own input. Oh, okay. So this is where I was telling you about the exception to the circular dependency. What do they actually want me to do? I'll put red on even ticks and green on the odd ticks. So odd ticks would be starting with first. I think all we need to do is get a NOT gate. So it feeds green. Does that work? Okay. Cool. So yeah, the reason it's able to feed into itself is because the delay means that the computer can still determine what like the output will be. So it says like, let's start this over. So it's red. So the output is currently red, or the output next tick is red. So it's green now. And so the next tick, the output will be green. So now it's red. The next tick, the output will be red. And so it's always able to tell what it will be next turn. Whereas if there's no delay, it can't determine it. All right, the bit switch. Component output different values on the same wire, you get an error. Okay. Using 2 NOT gates and 2 switches, build an exclusive OR gate. I'm going to explain what they meant real quick. So if you have 2 gates connected to a wire, it's not necessarily a problem unless they both try to put a value on the same wire at the same time. And then in that case, you get a short circuit. So like if you had 2 gates, let's pretend these NOT gates are something else, and you had 2 switches, the switch isn't going to let the gate output until it's fed a value here. And so you can only have, like, you could only make it so one gate puts a value on the wire at a time. That's pretty useful.
And with what?
There we go. Okay. So take a switch, take a NOT, wire the output of the NOT to the top of the switch, take one input, put it to the NOT, take the other input, put it to the switch. Yeah.
And what's
So,
up with
then you
the
take
song
the other two.
genre?
And just do it to the other inputs. So this one going to there. That one's green, and that one's green. So now we can put these both onto the same pin, which is essentially the same as putting it on the same wire.
And so you
The
want
reason
to
it's
do
not going to cause a short
voice?
circuit is because only one will ever write at a time. That one's ready. Now that, I guess they're both ready. Wait, no, this one is not writing. It's just weird that it's showing the arrows going in this direction, but it's not. It's disabled. All right. So next up is saving gracefully.
And why do you need a high voice?
Delay line only allows blah blah blah. you have two inputs. When the first input is green, update the saved value. And when second input is the value, okay. Obviously output what is currently saved.
And you don't have the money to pay for someone.
So what this is called is a D-latch. I'm gonna have to look up this.
So either try to find someone that will do it for free with you, or just do it with a deeper voice until you have the money. So I had a feeling that you're trolling. Yeah.
Schematic. Alright, so two AND gates. One NOT gate going into the input of this AND gate. That's save, so that goes into the NOT gate. This goes into
Nah, man. That will look
some space
really bad on me.
these two, I believe, are connected. Right. Okay.
You're 14, right? Or something like that. From what I remember last time you talked. Unless you're lying, which could be possible, but I don't think so. But I think you are younger.
Or okay, no. One input goes to both AND gates. And then this goes to that one. There we go.
How old are you?
I think this is our like the enable.
Yeah. So you're too young, man. But if you want advice, I can give you my advice when it comes to that, but I can't go on a call with you and then talk about this stuff.
It's the value. Well, we'll see how it goes. So next one is not or. Yes. Two not ors. Just wire the AND gates into the.
It's not because what you're gonna say, just it looks weird. Like being in a call with a 13-year-old kid talking about sex is strange. I don't want to do that. I give you advice here if you want, but that's as far as I go. And yeah, I'm not sure how valuable my advice would be as well. You said you want a girl moaning on your song. That's pretty much that's
out
very
of the NOR
sexual.
gates. Then you wire the NOR gate to the other NOR gate. Now you need a timer that I left over there. Wire that into there. And then I believe you can also just run that to the output. Let's step through and see if we've done this correctly. Nope. Okay, what am I doing wrong? Saving too long. I might have this output wrong. I need to run it off of this. That doesn't work at all. Okay. There we go. I had the wires hooked up wrong. I had the save wire to the value and the wire value to the value wire to the save wire to the value. Okay, say that 3 times fast. All right, so next one, I think we'll do the byte or byte not. Those might be the last two for the episode. I don't want to make it too long. I'm just do a two-parter. Right, so byte or. So yeah, if a byte from or if a bit from either one of the bytes is on, then we need to output it. So first off, we're gonna have to split these. Bring them back together in the end. Okay, so now we just need 8 OR gates. One for each byte. 6, 7, 8. Just wire up 1 to 1. I'm gonna color code this just for fun. It's a good habit to get into. Makes it much more readable. Right, simple as that. Run it. And then we can knock out the byte knot real quick. It's literally the same thing, but even easier. So now we don't even need to worry about having 2 pins per bit. It's gonna bother me. There we go. I won't worry about color coding these ones since it's so simple. And there we go. Let's take a look at bit inverter. I don't remember if it's going to be hard or not, so when invert is green, output the opposite value, otherwise just output value as is. So this is easy.
Nice, man.
Guess that's our invert bit. I think we can just use a switch, but we don't have it. Okay. Well, then we can just use exclusive OR. So this is our value on the top, and then this bottom one is just our toggle. See it, if you just think about it as this always being sent, and then when you turn this one on, it gets inverted. It's kind of just a different way to conceptualize it. An exclusive OR gate is essentially just it's a toggleable NOT gate. So the NOT gate is turned off, and then the NOT gate is turned on. It's just that easy. Yeah, and he even mentions it in the whatever it's called, splash. Cool. All right, let's knock out adding bytes, and then we'll be done for part 1. Add the 2 input bytes. Each
Cool.
output
Show
bit
me
in the output
when you
to-
have something, another song, or you improve the previous one.
result of the addition of corresponding bits from the inputs, and potentially a carry. All right.
I'm not
There's
sure
also
how
50
hard
bits from
it
the
is. It's
output
probably
table.
really hard to build
Finally, there's an input carry as
music.
well. This is useful for chaining together byte adders to add larger numbers. Yeah, they gave us an adder here, so we'll just pop down 8 of these. 4, 5, 6, 7, 8. Takes quite a lot of space. Have to split our bytes and then put them back together in the end. Carry just goes into the top. All right. Let's color code this again. 1 bit 1 to adder 1. Back this up a bit. Yeah, there's really no nice way of doing it. Just gonna have to make some spaghetti sometimes. Bit 2 to bit 2, or bit 2 to adder 2. And notice I'm leaving the top pin.
I don't understand what you mean by that.
Like I was showing you in the full adder part. How it just gets sent down through the rail.
Oh, you're learning how to play this song. Okay.
Right, just run our carries back like that.
I always liked saxophone on electronic music. I think it
Carry
sounds really
out
good.
The quote-unquote 9th bit that we can't use. All right, welcome back.
This actually sounds really good. That you might think. Yeah, thanks for sharing this, man. I actually enjoy this music. I like this type of music. You would be cool if you did an electronic version of this. I think that would sound really awesome. Obviously, it would be difficult. You'd have to spend a lot of time on it, but I think that's something that is a very good idea for people is to translate this kind of music into a more electronic sound, because it's a very similar things, but obviously it changes the music, but I think the essence of the type of music is kind of the same. It's just different times, different frequencies, so different times, so the music changes, but it's kind of like the same thing. Yeah, alright. Keep
All right,
watching
welcome
this.
back. Episode 3
Josh.
of the walkthrough.
But
the second half of
nice
the
music,
arithmetic
man.
and memory section. So let's get started with input selector. When the bit selector input is off,
If you ever
output byte
translate
A,
that
otherwise
into
output byte B.
electronic, send me the link. I'll definitely
Which one
want
of these
to
is
listen
A
to
and
that.
B? Okay. Top one.
Yeah, and I saved
So
this
what
one
this
for
is also called is a
listening to
multi,
later
or just a
because
mult for short.
it sounds really good.
It's not really important that you know that, but just a little piece of trivia while I get it set up. It sounds more complicated than it is, I think. Essentially, what we need to do is use switches, and we use 8 switches, one for each bit on each byte. And we've got, so like, let's say this is a set of 8 switches. We got 8 that are just on by default, and then one a not gate down to the other 8 switches. And so I'll just set that up in, what's it called? The opposite of slow-mo. All right, got the first part set up. Now we just need 8 OR gates to combine all of the bits. All right, and there it is, my my multiplexer. Let's see if it works. Oh, it's probably backwards, I imagine. Answer is 33. Correct answer is 34. So yeah. All right. Well, instead of changing that all, I'll just put another not gate in. Just a quick and dirty fix. There we go. See, we unlock the multiplexer. All right. Next up is negative numbers. This is one of the ones like the binary eraser where you just have to figure out the doodads. This one isn't a time trial. You just got to figure out how to do it. And I think I mentioned this before. Actually, maybe not. I think I edited that part out. So essentially, with a signed, is what it's called, signed representation. It just makes the 8-bit represent negative 128. So if you got that, then your value is negative 128, and then you work towards 0 with the rest of the bits. So add 1, negative 127. Then as you keep adding, you get closer to 0 until you get to negative 1. And so that way you can represent every number from 127 to negative 128. So gotta set this back to negative 1 and hit test. Boom. That's all there is to it. All right, let's go into signed negator. Input is signed, blah, blah, blah. Make a component that takes a number and negates it. Okay. So this is actually really easy if you know how to do it. And don't feel bad if you don't understand it. I was talking to someone recently who is completely aware of like the logic behind it, just wasn't able to figure out how to make it happen. So essentially all you need to do is take your input, negate it, add it to an adder, and just add 1. So when you use this always on and just use a bit wire, it's just going to input a 1, like a literal binary 1 in the first digit as well. So it's like not even like a third digit one where it actually represents 2. It's just representing 1. And output the value. See, we input. I'm gonna spread this out actually, so you can see the values, the byte values that are actually going into a component. Oh, up here, turn this to signed, so you can see 1 coming in, and it gets negated to negative 2. Then spread that out. See, negative 2 plus the 1 that's coming in here, resulting in negative 1. 33 to negative 34, add 1. That's all there is to it. And that the +1 all comes from the 8th bit being -128. Is there? I don't believe it'll let me show it.
And see on my thing if it's the same. And this thing there's too many levels and they don't have the name. Okay. Oh, so yeah, I did the same way.
So you can go from -128, but you can only go up to 127. So that one value of disparity is why you need to add 1 to it here. So yeah, hopefully that makes sense. Look up 2's complement if you need more explanation. All right, on to the bus. This is, okay. Something has 2 byte inputs and 2 byte outputs. Your goal is to copy from one of the inputs to one of the outputs. So it's basically first bit determines which input you should copy from. Second bit determines which output you should copy to. All right, sounds like a job for. Oh wow, just not even much of an option there. All right, so we want to have 4 switches. So these 2 switches are going to handle which one we pull from, and these ones will handle which one we push to. And just use these. Okay, output. That bit of a bit to the side. Okay, so one of these needs to be negated, and the other one is just a straight value. There we go. And hook up the byte. And there's one step you might overlook, is you need to, since you need to be able to write to both from either one, you need to connect it in the middle. So let's step that by one. So we want to pull from one, and we want to write to one. So I believe this is 1 and 1. So yeah, just switches are enabling, and it's just going straight across. All good. There we go. Here's a different one. So it's pulling from 0 and it's writing to 1. So cool. Just that easy. All right. Next.
I don't remember doing this. Yeah. So I think this one they added no. Before I did it. I think I'm just gonna copy the guy. There's also a couple of more there, I think. Okay. I wonder if they changed this because I did the video. I guess the other levels are the same and he doesn't have it because he's getting the later version. I don't remember doing this as well. So, but I think I might have done. Yeah, try it, man. Let me know. Share it with me. I'd definitely be down to play your stuff on my stream. But you have to work on it until it's really good. And I'm just gonna give you honest feedback if I don't like it. So. Oh, I have to go back to the other one. I think it was this one. So as far as this. No, I'm definitely not gonna play Roblox. There's too much stuff to do, man. Can't play games. I think this space turns this. Forgot what this one is as well. So I did something wrong. What's wrong with this? Switch. I think I'm gonna put this on the other screen so it's easy for me to see it. Let me do exactly the way that he did it, so. And now it's exactly the same, I think. Maybe it's a different. Maybe they changed the level.
Need to connect it in the middle.
Oh, I didn't see the end there.
So let's step that by one. So we want to pull from 1, and we want to write to 1. So I do believe this is 1 and 1. So yeah, just switches are enabling, and it's just going straight across. All good. There we go. Here's a different one. So it's pulling from 0 and it's writing to 1. So cool. Just that easy. All right, next one. Saving bytes. Create a circuit that can save.
Yeah, now it should pass.
Here's a different one. So it's pulling from 0.
Hmm. And what's wrong with this one? And this part is correct, I think. I don't think it's gonna work. Yeah, I have no idea what's going on.
0 and it's writing to 1. So, cool. Just that easy. Alright, next one. Saving byte.
I think I'll just move on then. Whatever. I'll wait for this one and then hopefully it's gonna work.
Create a circuit that can save or load a byte. And the first input bit is green, load the memory and send it to output. And the second input bit is green, save the input byte. The output has an enable pin, enable only on load. Okay. We don't have a register yet, so we need to do this bit by bit. 1 bit of memory, so we need 8 of these. 3, 4, 5, 6, 7, 8. Okay. Put this up here. Got to split the bit, or split the byte rather. The value goes to the bottom corner. We'll wire these up. I'm not gonna bother color coding these. There's not many like wires crisscrossing, so not too big an issue. And then when we want to save, that pin gets enabled, so we just wire that down to there. Well, I'll color this wire, so we'll have that at least. We'll just make it pink. That one's gonna break. There we go. It doesn't like these little notches. You're not able to run wires underneath. Oh, oops, I put it to the wrong one. There. I think that's right. Okay. Now we need to put this back into a byte. Good. I'm gonna do it like this and just run it up like that. And then this is our load pin, so we connect that to the enable pin there. That is about it. Let's check it. Nice. Alright, the next one, the 1-bit decoder, is super easy. We need to create 2 outputs from 1 input, and as you know, it's basically all you need. Just a NOT gate there. Boom. Just create 2 input, you send the original, and you negate it, and not much else to explain there. Alright, 3-bit decoder. So this is the same logic, but it's much messier, because now you need to take each one of those two options, but spread it out among 3 inputs instead of just 1. Okay. Well, I think this one here, yeah. I'll put down the 8 AND gates. 4, 5, 6, 7, 8. And so essentially what we need to do is take each input, run it to an AND gate, take its inverse, run it also to the same AND gate. It's actually way more complicated. I think it's going to be easier if I build it first and then explain it. So do that fast forward.
Yeah, maybe I should. It looks like it's gonna be hard, so I think I'm gonna try to build it alone. I'll put the video here and then just try to copy what he's doing there. Oh, that's actually correct. So 4, 5. It's kind of hard to see the video. This is a game called Turing Complete. It's pretty much a game where you build a computer from scratch. Uh, yeah. Each level is you have to figure out, it's kind of like a puzzle. And then after each level, after you solve each level, they start adding the components you've built before, so you can build more complex stuff. And then at the end of it, you have a working computer. So it's very, very, very difficult. So I think the other one is the same way. I also forgot to see what the other one does from the previous level, this one. It was just a switch. I think it changes the outputs of the bits, of the 8 bits. So the middle of this shoe with this shoe, I think. Hopefully I'm doing everything right, so I don't have to... I guess I can always create a new one. New schematic. Did I miss a step here? Oh, these ones are in the middle. He did the pink one super fast. So it starts at the second and then jumps one by one, I think. Yeah, this is gonna be super hard actually to copy what he's doing. It's very confusing. if you think it jumps one. And now it's connecting the other ones. So the other one is the middle there. I did it with different colors. Oops. Oh, actually, it's this one. And the one in the middle. So the green one.
All right, so
I think another thing that I'm gonna do once I finish with all of this is search one by one what it is and search videos. It's gonna help me understand better. And hopefully this works. Oh no. So either I did something wrong or his video was outdated, which sucks. So this should be on. Oh, so maybe is the place that I'm putting this. Should put here. Or this should be the green one, maybe. I think this should be the green one. Doesn't work. There's the one in the middle. Oh, think it crashed. Okay. Oh, this one, I think, should be connected to this. Maybe that's the difference. It starts here. Oh, nice. Oh, thank God. Yeah, so the biggest thing is that I don't understand what's the purpose behind these things. So I should probably watch videos, I think, of the description of what a 3-bit decoder is supposed to be useful for. But I think since there's still a lot of them, I'm not sure how much time it's gonna take for trying to do all of them. I think I'm just gonna go as fast as I can just to see them all. And then after that, I decide whether or not I wanna watch the videos because I'm probably gonna watch the videos from Ben either way, talking about the hardware. So, your device I can or NAND, NAR, and true inputs. Instruction is just what we call the number that determines what you compute. Mm. Oh, this is the one that I just did, I think. No, the one that I just did, I think it was the 3-bit decoder. So this is from a previous level, I think.
Here we are. This is quite a mess, but it's not so bad. If you're trying to parse it just piece by piece, I try to color code it to make it easier. See these, the top four and the bottom four are each grouped together, like with these purple ones, and each of those groups are getting the, well, one group is getting the inverse of this bottom bit, and the other group is just getting the normal one. If you look at these center pins, like with the light blue, there's also a set with the orange getting their center pins, like the orange going to the center pins of these four. Those are also opposites, so the light blue AND gates are getting the opposite of the AND gates with the orange. And then the last ones, the ones with the dark blue on the top pins, and then the ones with the bright pink on the top pins, they're getting opposites of each other. So it's the same logic of sending a normal and an inverse bit to, the gates. It's just a lot more messy with more bits. But yeah, it works. Da, 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 da. Oh yeah. So this unlocks a 3-bit decoder, but it gets a disabled bit on the top, which comes in handy later. So yeah. All right, the next one is one way.
Oh, I think it doesn't have this level here. It's probably new. Yeah. Or maybe it's this one, actually. I think I'll wait and then I'll see the other ones. If it doesn't, I'm gonna search for someone else.
All right, the next one is one way. This one is super easy. Essentially, you just have to make sure that data doesn't flow back
I
from.
think what I'm gonna do actually is after I'm done here streaming, I'm gonna do the rest of them, or as many as I can off stream. Because then I can put one window in one screen and watch the video as I go. It's gonna be a lot faster.
The output. And there's like, a million different ways to do this. But I think the best way is to use an OR gate. Just pop it like that, and so just go straight through. The other easiest way is to use 2 NOT gates, and like that. Since it just inverts it twice, it returns to its original state, but why use 2 gates when you can use 1, right? Alright, so this one, little box and counter. I feel like we should end with little box. I think counter will be much easier. Yeah. Build a counter that will increase by 1 each tick. Additionally, there should be an option for overwriting the counter with a given value. You are given 2 inputs, a bit and a byte. The bit input should toggle between counting and overwriting with the value of the byte. Right, so the bit immediately screams to me that a switch is involved. Counter. Probably an adder. Yeah. What's this? Oh, we got a register. Yeah, that'll be necessary. Switch. So the switch is going to toggle between whether the adder goes through or the input byte. Or wait. I don't think that's going to work. Because these are both going to write at the same time and cause a short. Well, instead of a switch, let's use a muxer. And it doesn't matter if they write at the same time. Put that there, put that there. This bit toggles the muxer. Goes into the register. Oops. Save and load. I'm guessing load, it should just also, or it should just always be doing both. Is there any time, am I just always supposed to be outputting? I guess so. Okay. I'm gonna rotate that, just to make it a little sexier. Yeah, it's pretty tight solution. Let's see if it works. Nope. Okay. I might just have this backwards. Register is going to the output, which goes to the add, goes to the muxer, goes to the register. No. Oh, I don't have a one going into the adder. Let me just wrap it around. There we go. I kind of regret building it like this because I realize it might not be the easiest for everyone to see. So I'll do my best to explain it. What we have is the adder. The adder is getting a 1 from this always-on signal. And so it sends, let's start over. So it's sending a 1. It starts off by sending the 1 to the muxer. The muxer, by default, pulls value from the middle pin. When this is turned off, it pulls from the middle pin. So when it's off, it sends the 1 from the adder to the register. It's step through, we'll see that, it goes in there. And now the 1 is going to go into the output, and then also back to the adder. There it goes, went into the adder, and now 2 is coming out. The 93 from the input is just going to waste because, well, it's not going anywhere because it doesn't get sent until this turns on. So the adder will just keep ticking up, 3, 3, 4. Let's go until we get a signal from the bit. There we go. Okay, so this turned on, which tells the muxer to pull the value from the bottom. So now that got sent through into the register, and that's going to get sent into the output, and also into the adder. You might wonder why would you want to lose the number that was in the adder before, but this mechanism is integral for running a program. Stick around long enough and you'll see why it's a bit too much for me to explain here, because we still have to go do the little bots. Let's go do that. Can you fit 4 bytes of memory in this limited space? Blah, blah, blah. Okay, so the solution I have, like I'm using as a reference, that I made it myself, and it's a bit too small for someone watching a guide to really see what's happening. It is a bit unreadable. So I'm going to do my best to spread it out a bit. So we got 4 registers here. Then we're going to take our output. We're just going to connect them all to the output. We can actually just connect them together like this. Because the way we're going to design it, it's only going to have one register load data at a time, so we won't have to worry about a short circuit. Okay, now move it down. Let's move this like here. Yeah, we'll get our input up here. Now that's just going to run to all the value pins on the register. So this is what's called a bus as well. So you're just putting data on one common line that these will pull from when they're told to, and then they'll push to this bus when they're also told to. Now we will get, okay, let's get this going. Get 4 switches. Actually, let's start with 2 NOT gates. Put that like that. And those of you who are paying attention might notice that these are each a 1-bit encoder, and we're going to be adding them together to make a 2-bit decoder. So that's what we're going to do now with these switches. I'm actually going to move them to this side because switches just naturally tend to move to the right. That's the way they are made. And then let's do something like this. Okay, so we have A0 turned on right now. So let's just say this register is A0. So we want to turn that one on. Let's wire up these switches. So now that register, now this switch is turned on, and that's the switch that's going to go to this register. I'm going to rotate it like that. We'll put it over here. Oh, you press spacebar to rotate, by the way. I realized I didn't say that before. Okay, there and there. So that's A0. Now, this is going to be B0. It could be A1, but I think it makes more sense for it to be A0, B0, A1, B1, in my opinion. So let's turn on B0. So now that's B, and this is still 0. So we wire this one up to the pins that are now turned on. There we go. Now the next one will be A1. Wire it up to the pins that are on. And then B1. Boom. Now, what we can do is just take this pin here and wire it straight to our load value on each register. Or can we? No, I don't think we can. Sorry, that's the next step. So this is our 2-bit decoder. This tells us which register we're going to be working with. So we know it's just going to be this one, because this one's turned on and no others. So now we need another 4 switches. Let's put them here. I'm actually going to move these to the right one. Yeah, there we go. Now wire this down to the top of that pin for each register and take our input. Okay. So we've got this load one on the bottom and our save on the top. Now we can just wire this load straight to our output because we don't need to tell the registers to load because we're going to do that here. So this is the step that I had mixed up with the last step. So every time we access that register, it's going to load it, and we just tell the output to load a value when it's ready to. So, you know, you could make it so that the register loads a value when it's supposed to, and then this just always is taking whatever input is given it to it. But this just works better because it uses less switches. I suppose you wouldn't know that without already seeing the other solutions, but this is a good solution. All right, so this is the save pin turning on, which will, well, tell the switches to turn on, but only if they're already getting this signal. So you can see how register B1 is getting signal from here, and then getting the save signal from here. And so it tells this register to save the value that's on the bus. And it's also being told to load. And yeah, I believe that's it. I don't think I've miswired anything. Let's give it a run. Nice. So yeah, I'll throw up the solution that I've got. It's the exact same as this. It's just packed together much more. And, you know, it's functionally it's no different. I just find it fun to make it as small as possible. Actually, I think that'll do it for this episode. I don't know if we'll be able to do all of this in one go. I'm probably going to be
If he doesn't have the level, I'm gonna search
Hello,
for
welcome to
other
episode 4.
person. I was thinking about doing 20 minutes for each level, but I don't think I'm gonna do that anymore. There's just too many levels. It's not worth. It's better to just try to go as fast as possible and then think about it after I have all the levels unlocked, because then I can study one by one. I think that's a better strategy. And then I can move on and focus on the Rust stuff and watching these videos here as well, which is gonna be more practical. And also, I think I'm gonna watch assembly videos as well once I finish everything.
Hello, welcome to episode 4, I believe, the Turing Complete walkthrough. Getting started on the CPU architecture section. So let's just get right into it with the logic engine. Okay, so we've got created a device that can OR and AND, NOR or AND 2 inputs. The third input will be the instruction. An instruction is just what we call the number that determines what to compute. Instructions OR and AND, NOR, and AND.
One of the things as well that is kind of hard is that you kind of lose track of the previous levels. And this is especially true for me because I stopped. I did them months ago, and now I'm coming back to them. So I've kind of forgot about a bunch of things, and then it starts building up. But because it took so long for you to move up, you kind of forget what each one means. So I think that's another reason why it's probably going to be better to just go over them as fast as I can, and then study all of them so I can have an understanding, a clear picture of how everything connects with everything.
And also, you can't move the right components in this level for reasons that will be revealed later. All right, so let's start off by decoding our instruction byte. All right, logic, we need OR, NAND, NOR, or AND. So if you remember, the AND is just an inverted NAND, and an OR is just an inverted OR. So I believe, yeah, we got the byte logic there. We don't have the AND or NAND for the bytes though. So let me get the schematic for what a NAND actually is. Here we go. OR and NOT. So you look here, an AND gate is just 2 inverted inputs with an OR gate and another invert, or another NOT gate technically. the NAND gate here, it's got two NOT gates for some reason. You can get rid of both of these, and that's why I said in the first episode that an AND gate is just an inverted NAND gate rather than the opposite way around. So yeah, we just need to build a NAND gate and then invert it. So let's get our two NOTs. Just wire that up to, I believe both of the bytes. There we go. Or those together. And we can put both of these into our OR gate as well. That'll be for that instruction. Right now we've got 2 bytes here. This is our NAND gate and this is our OR gate. So let's go ahead and take a muxer to combine these two. And now we can toggle between either taking the OR instruction or the NAND instruction just by turning this muxer on or off. But also, what we're going to do is we're going to take another NOT here, put it down there, wire the muxer to that, and then bring just the original output here as well. We're going to get another muxer, connect them like this. So now when we turn this one on or off, it'll choose between the normal input and the NOT input. If you're not getting your head around this right now, don't worry about it. I'll explain it when it's all put together, and that should be easier. Right, so what are the instruction numbers exactly? Okay, so 0 is just an OR. So by default, we already have that, because the muxers will take the middle pin by default. So that's already going through. If we send a 1, we want to take this one, so we can just run that to this muxer. See that? Yeah, so I don't know why it doesn't show a red signal when I turn this on. It will work though, see? Just have to remember that it is on. So that muxer turns on, it takes the input from the NAND gate. The NOR gate is next. So that means we want to take the middle pin from this muxer and the bottom pin from this muxer. So let's hook that up like this. So we turn that on now, it'll take it down there. And lastly, the AND. So with the AND, we want to turn on both. And actually, that's already, it already works like that because it's the third instruction, and binary, a 3 is 1 and 1. So both of these will turn on green, which will turn on the muxers. So let's step through. All right, first one, we want the NAND gate. You see we're getting to 31. Binary, like doing the OR and type operations on bytes is slightly different because you're operating on an entire byte of bits. So I'm just going to use an example. Let's say 1011 and 1100. Let's say we're running the NOT AND operation. And so you process each bit individually. So all of these ones, this will be 1 because that's a true in the NAND logic. 1, 1, 1, and then this one is AND, so that's false. And so that's what these 4 bits NAND together looks like. If we did NOT, actually that doesn't make any sense, not because the NOT is a unary operator. Say NOR. Well, each one of these have at least 1, so this would just be 0, 0, 0, 0. So that's why like the output is going to look different than the inputs. But you can see here that 231 is coming out of this little NAND gate, and then it's going in here. Let's spread this out. Okay. So you can see 231 is going into this NOT gate, and it comes out as 24. But the muxer is taking the 231 and sending it out. 46, that is coming from the NAND gate again. All right, 254 is coming from the OR gate, right there. Here we go. Here's the AND. This is what I wanted to see with the 2 pins. So you got 32 coming out here, and that's coming out here because the NAND is sending 223, and then that 223 gets inverted inside the NOT, which sends out the 32, and this muxer is turned on, so it takes the bottom pin, sends it out. So yeah, it's a nifty, tight little circuit we got here. Nice. All right, next up we have the arithmetic engine, which is just building on top of our logic engine. So now we got the same 4 instructions as before, but now we also have an addition and a subtraction. So it's sending 223, and then that 223 gets inverted inside the NOT, which sends out the
I think I'm just gonna watch this video and then do this off stream. It's just a lot easier. I can use the 2 monitors. Yeah. I'm gonna try to do as fast as I can and try to finish today, probably all of them. See the levels. Well, if I don't finish, I think up to here I probably can finish. So what I'm gonna do is copy this stuff, watch the videos and just copy everything. And yeah, maybe after each level, I'm gonna try to finish until here today. And then tomorrow, or maybe Sunday, I'll come to this, and then I also think I'm gonna do a spreadsheet with all the levels, the names. And then I'll study one by one what each thing does. And then once I got done with that, I will go back to watch the videos and finish this and do the same thing until I get to the assembly thing. And then that's gonna be a good point to start watching videos about assembly.
32, and this muxer is turned on, so it takes the bottom pin, sends it out. So yeah, it's a nifty, tight little circuit we got here.
I have no idea. Let me think about it. I don't know, man. I'm out of ideas.
Nice. All right, next up we have the arithmetic engine, which is just building on top of our logic engine. So now we got the same 4 instructions as before, but now we also have an addition and a subtraction. So let's get our byte adder. And if you remember how to negate a byte, then
Bomba? That sounds, bomba is explosive in Portuguese. Yeah, it's a good name, I think.
essentially you've already got some subtraction built in, because subtraction is just the addition of a negative number. So if we take,
Oh, one idea that I had about the your girl thing, the sounds. Maybe you can find something online. I haven't thought about that, but it might be possible that you can get these kinds of sounds from other people. I imagine that there are probably softwares or people that provide their voice online or something like that in exchange for royalties or something. Or I don't know, but maybe there is something like that.
just our first, let's get a different color for the logic or the arithmetic part. So if we take the one byte and put it into the adder, then we can take our second byte, also run it into the adder, but also run it into this negator. Let's get rid of that because we need to use a muxer now. Spread it out a little bit. This muxer will tell us, or it'll let us choose between addition and subtraction. Because when the number goes through this negator and gets sent through into the adder, then it'll actually be performing subtraction. You're just adding.
There's also a very good idea, I think, that came to my head, but I'm not sure. I don't have time to do it, and I'm not sure if anyone has done it. But I think it would be maybe it would work to do something like kind of like Spotify or SoundCloud, but on Web3, where people can post their stuff and their wallet, and then maybe you can have NFTs, and then people can collaborate based on that. That might be a really interesting idea.
The negative number. All right, so what's our instruction for, that's addition. So we don't, okay. Well, we will need to get another muxer here. And that muxer will decide between either this set of logic or this set of arithmetic. Connect these up. So add 4, run that down. Subtract also needs to be included. So if we use a AND gate for that, we'll actually use a switch. If you think about it, a switch is actually just an AND gate in disguise. Oops. Right, because this will only be green if both of these are green, which is the exact same truth table as an AND gate. So it's just a smaller AND gate. Now we need to get this muxer hooked up. Just run subtraction. So this is the same subtraction line. We just run it off of this. That's pretty ugly. Run it. That.
No, it's better if you send the link. Not gonna download the file. And I don't think I'm gonna watch it now because I have to watch this stuff here. But do a YouTube channel, man. Like you don't have to show yourself or anything. Just create a YouTube channel and then post the stuff there, and then share the link. I think it's a lot better. And I think YouTube is probably better than SoundCloud, I think, but I'm not sure, obviously, because I haven't studied that or anything like that, but I think YouTube is better because more people use YouTube and it's easier to share. I think it just makes more sense.
I don't like how it's covering the byte. Okay, that'll work. So 4 needs to go to this muxer, but also, actually we don't need to switch here. We only need to switch for the muxer, because this will turn on in both cases for addition and subtraction. So let's go ahead, make some space there for a line, run that to there, and then also from the 1. That goes to the mixer. Okay, now we got the number coming through. Apologies for that oversight. There we go. All right, looks like it's taking us straight into the component factory. All right, so yeah, you just can, it's kind of like sandbox mode, but this is for making stuff that you'll actually use in your overall like completed computer. So yeah, it's pretty useful. All right, let's take a look at the registers. In this level, you need to create a circuit which can copy from a source to a destination. The instruction byte in this level determines the source and the destination. Bits 1, 2, and 3 give the destination. Bits 4, 5, and 6 give the source. Source and destination can be one of 6 registers. We will name them register 0 to register 5, respectively. Additionally, this map has a dedicated input component, which can be the source, and an output component, which can be the destination. These are the bit patterns for each source and destination. To get a more intuitive understanding of the requirements, click the instruction icon in the upper left corner. All right, this is confusing at first, but once you start wrapping your head around it, it's not so bad. So first of all, we're going to make a bus. I'm going to use light blue for the inputs. I'll use the pink for the outputs. Wire them up. Now, another important part of this is that these two buses need to be connected. Let's wire that like that. They might need to be connected on the top. We'll see.
Maybe it's better to not annotate on a spreadsheet now that I think about it, because it's probably better if I look at the level and then research the name. Because if I just write everything down, I'm just gonna forget how it looks on the circuitry. So I think what I'm gonna do is next time I'm gonna go through the levels that I already done on stream, and then after I go through the level, then maybe I can write it down in spreadsheet just to keep track. Then go through them and then research what they do. What's the point? And there are some new ones as well that I didn't do, like this one. So I think it would be good to review all of them.
Later. But let's just wire these up to the inputs of the registers. Alright, so now let's take a look at this. Input. Register 1.
I'll
2.
listen to it after the end of the video, man. I have
Okay,
to
who's
focus
there?
on this,
So let's
finish this
I think
fast.
decode this. Maybe we should just use the decoder first. 2 3-bit decoders. I think I just wired 1, 2, 4 up and then.
But next time, post it on, make the YouTube and post it there. It would be cool as well, because then I can subscribe to you and see your stuff. And see your growth as well. I think that would be interesting.
32. Yeah. Register 1 is this. So to say this is 0. So register 0 is just it'll be this one. It's not turning on now, but that's because it's not hooked up.
Next time, make a YouTube channel and then post the songs you make on the YouTube channel. Because then I can subscribe to your YouTube channel. You send me your YouTube channel. I subscribe to it, and then I can see your progress. I think that would be interesting.
Source. Okay, so source is 32, 16, and 8. Destination is 4, 2, 1. So that means 4, 2, 1 needs to be hooked up to the save pin, not the load pin, which is the middle. Then hook this up to 3. 0, 1, 2. And 3. Run out of space. Let's move this bus inwards. Oops. There we go. 3, 4. And then 5. And just do the same for the destination, except you're running on the load pins. Or, no, I'm sorry, this is the source, not the destination. Make this a different color. Let's see, why not this? They're around the pins. And the last one there should be output. Yes, or not output. Cool. I believe that will work. Like I said, I don't remember if I need to connect the top of the bus, but the bottom is necessary. As far as I remember anyway, we'll try it out one with each. Register 0 should have value 0. Okay. Oh, I didn't hook this up to the input. Start over. There we go. Let's try it without connecting the bottom of the bus. I'm pretty sure it's gonna fail. Yeah. I haven't mastered busing yet, but so I don't exactly know why this doesn't work. Expected output 63 got 0. Oh, I see, because it wanted to just load straight from the source. Okay. But yeah, not too hard. I'll just do a quick show of it in case you want to screen screenshot it and then copy it over to yours. All right, next up is the instruction decoder. So this is essentially what we were using in our arithmetic and logic engine. So let's do that. Start with splitting this byte. We only need the bottom two. So we want, when neither of these are true, we want this one to be true, turned on. So that's just a NOR gate. We'll put these on a bus. I'll do this dark orange for the 64 bit. And I'll do the blue, light blue for 128. So I can both up here. There we go, that's turned on. Now, calculate is when 128 is off, but 64 is on. Here, let's zoom in. So that's just a 128 and not 64. So we can do our pseudo AND gate. If you remember the second tick level, this is the exact same concept. It's just one and not the other. So it is 120 or 64, 64, and not 128. Let's try that out. There we go. Exact opposite for the copy. So this will be 128 and not 64. Let's test it out. Oh, whoops. There we go. And the last one is just both. So it's just a straight switch. It's just that easy. Alright, next up is calculations. Alright, so we're going into calculations, but little disclaimer. I had to go back and redo all of this because during the calculations, my original recording, I got confused and I messed stuff up, and a lot of it was unusable. And essentially, like the part where the first part that was usable was very early on in the challenge, and the next part that I had to cut to because the middle was just me trying to figure it out. After that was I had already built too much to really explain. So this is all going to look a little differently. Mostly just this bit up here, but hopefully there's not too much of a difference, and it's pretty much the same as it used to be. Oh, the reason I had to redo it all is because you can't reset like the calculations and the register levels. They sort of like they're all mixed into one, so I couldn't just go back and redo the level. But yeah, let's get started with calculations. We need to add an ALU to here. We take values from register 1 and register 2 and save them into register 3. Remember, we start counting from 0, so this is register 1, 2, 3. So let's go get our ALU. Register 1 goes into the top, register 2 into the bottom. The top one takes our instruction. I believe that just comes off of the main bus here. I'm going to straighten that up. Right, the output will come down into register 3. We're going to need a switch on here to prevent a short circuit. Alright, pick that up. I connected it to this bottom pin because this pin will always output, whereas the other one you have to enable the load pin to be able to get the value out. I mean, we could do that, but there's really no reason to when this bottom pin is there for us. Alright, now we need to process these instructions. So that is what our decoder is for. I think we can just pop it down here. Alright, so now we want to disable all of these loading and saving pins whenever we're not in copy mode. So if we're not in copy mode, then disable. Just run a NOT gate. I'll make this gray. Then there's our copy pin, so we'll just run that into the NOT gate. So now every time we're not in copy mode, these will be disabled. And now we just run the calculation stuff. So this bit will use this like light green color. Just run that down to our switch. Alright, so let's see what we got. We got the ALU taking values from 1 and 2, it puts it in 3 when it's in calculation mode. The opcode is there. I'm not sure there's much else to it. Go ahead and try to step through. Okay. Register 3 should have value 2. Alright, we have to save, that's right. So save pin is in the middle there. Let's get an OR gate. Let's move this down. Well, actually we should move it up so that this can fit on by. And just connect this up. Right, now let's try again. Right, there it is, 255 in the register, and it seems to be alright. Yep. Alright, I'm glad that worked. I spent a long time getting back to this level to redo it. For the rest of the video, though,
I haven't listened to it yet. I'm gonna finish this video first, because I have to finish this stuff fast. And then after that I will listen to it, and then I'll stop streaming. But yeah.
gonna go back to how it was, but in the next video we'll be working with this architecture again. It shouldn't make any difference. I remade it so that it looks cleaner. So really this is a good thing. So yeah, we'll go on to the next challenge. Alright, next up is the program level.
What do you mean? The song?
The instruction input component has been removed. It has been
Our bombas, the explosives.
replaced by a program component. Every tick, use the counter to load the next instruction from the program's memory. You must use the counter component you unlocked earlier for this level.
No, obviously not. Who would like that?
All right, let's hook that up to the output. So if you may remember, I was telling you when we were making this counter that why would you want to, like when you overwrite, you lose your previous number that you had counted up to. And why would you want to do that? Well, because when you overwrite, you're telling the, like that number that you overwrite is now the address of the program you're running at. And so now the counter continues from that new overwrite address and keeps going forward by 1. So that's why you don't mind losing that previous value. Okay, so increment and overwrite value. Did it tell me I need to? Did I need to use the overwrite? I don't believe so. So I think, yeah, it just wants me to increment through it. But we will later implement an overwrite. So let's go. All right, let's take a look at the conditions level. I had to mess around with this one to make sure I fully understood it and could explain it well enough. And I feel like I can. So this level has a value input and 3 condition inputs. The 3-bit select the condition is shown below. Check the value against the selected condition and output green if it is satisfied and red otherwise. So if we take a look at
Yes,
these
I am. I'm a virgin.
are essentially just opposite. So whenever it's just this bit is on, then we turn on, or if it's not, then we don't. One thing that's annoying is that this bit on the left is actually this bit on the right, which is very annoying. But anyways, let's go ahead and split these apart.
Are you?
And what we're going to do is we're going to combine all these bits with NOR gates. And so if I can find it, there it is. So if all these are true, if we connect these up to their own pins, then that means the value is 0. So that's one of our tests here. We're going to just focus on the first half, and then the second half will just come naturally because these are essentially opposites.
Yeah.
So let's finish hooking these up. Then we'll use AND gates, are colloquially known as switches, to combine those. There we go.
Interesting.
Right. So now this will be green when all of these are red. Next, we just have to work on the actual comparison part. So whenever this bit like turns on its own, then we know that that bit just gets passed through.
It's fine,
So
man. You're young,
exclusive
so
OR gate.
doesn't matter.
Just wire that pin to it. I'm gonna
Even
route
if
it
you're
around
old, doesn't
the
matter.
outside just to stay out of the way.
Give us a shit.
There we go. Let me turn it back off. Okay, so if this first pin is on, then we output true if the value is 0. But we know that when this pin is on and this pin is on, then that's when we output 0 for that case. So let's go ahead and get a switch there. I'm gonna,
Yeah, true.
I'll just route it like this.
But
I'll
that
leave it out
stuff
there,
is bad, man.
I'll even color code it.
Just gonna destroy your life. So
So now that will be true when the output is 0. Next up is when this bit is on, then we want to be true when the value is less than 0. Well, if we're using sign notation, we know that whenever this last bit is on, we're going to be negative. So we can just run an AND gate. I'll move these out a bit. From this negative pin, the sign bit, to this pin. So now we know it's going to be negative.
yeah,
Now we can just combine these two with an OR gate. Put that into our exclusive OR gate. And I think that's actually about it. Let's test various circumstances. All right, so we got the middle bit is turned on. So if it is less than or equal to 0, it should be green. So we are less
Quit
than 0.
forever.
Let's see if we are 0. Okay.
use the energy for
see
working
what we're
out
missing.
instead. It's way better.
Or actually, I've misunderstood this, I believe. So it's less than or equal to 0 when both of these bits are turned on. So there we go. That's better. Never is never. Always is always. Equal to 0. Okay, so let's turn this bit on, and then this should turn on because it'll be true when it is not equal to 0. There we go. So the reason that it turned off is because this entire section is 0, which means this is turning on. So this is turning on our AND gate, which is going through into our exclusive OR gate, and it is turning off this signal from the 4. And so it's just like sort of naturally inverted because if you remember, the XOR gate is a toggleable NOT gate. So yeah, it's a nifty bit of logic going on in here. And I'll be happy to try to clarify anything. If you have a question, leave a comment, and I'll try to explain it. Let's move on. All right, one level before our working computer, immediate values. We need a way to directly move numbers from our program into registers. For this, we use the immediate mode. When the two highest bits are off, when in immediate mode, the whole byte is interpreted as a number that we save into register 0. This means we can save any value between 0 and 63. So immediate is this top one. And in that case, I believe we just use a switch, a byte switch. We'll give this the, just do
There
this
we
green
go,
there.
man.
So connect that to the bus.
Do a
And
daily
immediate-
routine thing.
We run this bit
That's
down,
what I do.
turn on the switch.
Every morning I have a small group, and we type our daily routines there. It helps after you keep going for a long time. Sometimes yeah. Cold showers are good because they force you to get out of your comfort zone. So, but I think everything has a balance. So sometimes it's not worth it. Yeah, that's good. Sure, depends on the situation, I guess.
We also need to turn this
Yeah,
on so we can use OR gate. So now the best way to
it
fix
doesn't
that.
matter. You can't afford gym. You can just do push-ups in your house. It's free, and there's also other exercises you can do. So
Here, but we'll manage.
yeah,
And run our bit up to there. That doesn't look too bad. Now we can just run our byte from the bus. I'm gonna go ahead and change this to just a normal blue. It'd be much easier to see everything that way. Alright, I think that's all we need to do is just putting value straight into register 0 when we're in immediate mode, which turns on the switch and turns on the load pin. Alright, let's give it a run. And just like that. Alright, let's move on to the working computer. Until this point, all possible programs have been confined to running in order, byte by byte. Before, only code could influence memory. Now, memory must influence code. With the addition of conditional logic, our computer can run any algorithm and calculate anything.
I bought a thing to do pull-ups on the door when we are on lockdown. And it doesn't break the thing if you install correctly, obviously. But it has to be the one that you actually make a hole in the door. It can't be just one that uses pressure because that one is risky. And it can be risky. I wouldn't do it. But there are other exercises you can do as well. You can put your feet on the chair and then pull yourself forward with your arms. And there's other stuff you can do as well.
The final thing we need to add is a mechanism for changing the program counter through instructions when certain conditions are met. When the two largest bits are green, we are in condition mode.
Yeah.
In condition mode, the value in register 3 is compared against the conditions.
That's
by the lowest
pretty
three bits in
normal.
the instruction. If the condition is true, we overwrite the counter to the value in register 0. Conditionally changing the counter means we can skip instructions based on conditions or have instructions run in a loop. Here's our conditions. These conditions correspond to the condition component that was saved in the component factory. So it's our... Where is it at? That is an ugly-ass component, but we'll make do. Oops. Okay, where should we put the program? I don't really like it being here, but... I guess it doesn't really matter. Alright, so condition. This outputs just a bit. So that'll go to our overwrite pin. Tells it to overwrite.
Why not?
It takes the value from register 0, so we just run a line from there. We'll use yellow, I guess. Take it from that pin.
I think it's pretty normal.
There we go. It takes the condition and an input.
It has been a long time since I don't play anything, but I think it's quite normal, and there are probably fun games out there. I'm not sure. But I think in your age, I used to skate as well. But also, I played a lot of video games as well. So I think you can do both.
The condition is... Okay, so that just comes from the bus. That's just like that, wrong color.
Yeah, that sounds like fun.
Move it over. And the input, what exactly is the input again? It's just a number. Oh, okay. This comes from register 3. That's right. So we use not quite yellow, but close. All right, I think that's about it. No, next to counter value be 0, it should be 1. So why isn't this loading? Oh, I ran it from the wrong register.
Yeah, that's the downside.
I ran it off register 1 instead of
It
0.
can get addictive.
Start over.
Yeah.
Still got an issue.
That's true.
Is... Oh, I never ran the condition bit. Okay. Yeah, if all the bits are off on the top, then it'll never be on. So we can just disable that top one with a switch. And that switches.
Yeah, good for you, man.
This pin. It's not gonna be nice. There we go.
You should figure out what you like, one thing, and then go for it. But I think it's fine because you're young, so it takes a lot of time to figure out what you want. Yeah, that's cool. If I were you, I think I would focus on programming because I think programming is gonna take over everything eventually. But music is also fine because it's artistic, so I don't think it matters that much. That program code's gonna take over. So I think that's fine. But I would focus on one thing for at least 2 or 3 years and go really hard on it before moving on to something else. I think that's better. And maybe try to. The idea that I had in the future was to make music with machine learning. That sounds really cool. So maybe it's something you can try. Yeah, that sounds really interesting to me. And I think there's already uh, machine learning algorithms that create music. And I think they're gonna get better and better.
Hello, welcome to.
Oh, so it's fine. So just focus on music. Are you using as
Switch is connected to this pin.
what software are you using
It's not
to
connected.
create music?
There we go. Okay, so that the condition pin turns on, then it turns on the switch, which turns on the condition component. Well, let's see. There we go.
FL Studio. Interesting. I'm from Brazil.
And just like that, we have a Turing Complete machine. Yay. All right, so that's going to be the end of this video. The next one, we're going to look at these programs. The maze might be...
I actually had a friend or that he actually did music. Oh, he was doing music, but it has been a long time since I don't talk with him. It's kind of hard to break through, but I think he's a people that usually do it, they really enjoy it. So I think most of them don't do it for the ones that really succeed, and they don't do it because they want some outcome. They just do it because they love it. So it's like they can't lose. Cool. I think I like this style.
Made it through the good and the bad times.
I like the style of the previous one more than this one, but it's also good. And I think one thing you could do is add more different sounds because it sounds kind of the same through the whole thing. But I guess that it's probably hard to do that, I think. But I think that's the best direction to go. To put more of. Because usually the best songs, they are kind of. They have some patterns, but it's not so much. is you kind of have to strike in between, I think. So you have some build-ups and then some things that are different, and then keeps the music interesting. Like it has to have some emotion behind it. I think this is too robotic for me, but it's also artistic, so it's kind of hard to tell because everyone has their own taste. On page in 2 days of the hard song. Cool. Yeah, I think I'm gonna stop here streaming, but do what I said there to create the YouTube channel and then post the music, and then we'll see. Um, I'm interested to see your growth. So, like I said before, next time I'm gonna do as much as I can off stream of this, and then next time I'm gonna go over one by one and research the concepts, and then yeah, and then do this over and over until I'm finished. And then I can learn assembly or watch videos about assembly and then go back to Rust. So see you then. Peace, Edison. Nice talk to you, man. See you.